for me. So I'm going to talk about compact subgroups of diffeomorphism groups and Jordan property. So let me begin by recalling a completely standard fact about Lie groups. If G is a connected Lie group, then it is well known that G has maximal compact subgroups and that these groups are unique up to conjugation. Okay? So in precise terms, what this means is that there exists a compact subgroup of G with the property that for any compact subgroup, call it H, there exists some element of the big group G such that the conjugate of H by this element G is contained in K. Okay? And then K is called a maximal compact subgroup. It is perhaps not so well known, but it is also true and not hard to deduce from the statement that I have written, that this is also true in case G contains finitely many connected components. Okay. Well, but of course this condition can be considered in much wider generality, namely whenever you have a topological group, it makes sense to ask whether this group contains maximal compact subgroups and whether such compact subgroups are unique up to conjugation. We have to keep in mind that these are different questions. Okay? So let me give now a general definition. If this G denotes a topological group, we say that this group is inner compact bounded and I will write ICD if there exists a compact subgroup such that for any compact subgroup G, H, there exists an element in the big group conjugating H to a subgroup of K. Okay, so well, I mean this name is not standard. I didn't find any standard terminology for this notion. It might sound a little bit awkward, but it will be understood why I call it this way when later I will introduce another notion similar to weaker, but weaker than that. Okay. Now, what is the main objective in my talk is. Well, I want to study which diffeomorphism groups are inner compact bounded. Well, first of all, for this to make sense, I have to specify a topology on this group because otherwise there is no it makes no sense to talk about compact subgroups. And the topology I will consider is the C infinity. But most of the things I will explain are also valid for C1 topology or higher regularity. Okay? And I will also consider the same question for subgroups of the diffeomorphism group of geometric origin. We will see examples of that. Excuse me?
Is this scale not maximum compact?
Yes.
Is it maximum compact?
Yes. This is a definition, and this is a statement, a lemma, property. Okay, this refers only to Lie groups. Okay, and now I'm extending the definition to arbitrary topological groups.
Well, what we know have maximum.
So it's the same as saying that there exists a maximum compact and that they're all congruent.
Yes. Yes. Okay. Let me make an observation that will be useful later, which is the following one. In that definition, I'm talking about compact subgroups of an arbitrary topological group, so a priori there is no reason to expect that such K need be a compact Lie group. Okay? But when we are talking about diffeomorphism groups, it is well known that compact subgroups of the diffeomorphism group are Lie groups. And I mean, it's not a completely obvious fact. Standard proof of this fact is the following. See, if you have a compact, any compact. If you have a compact subgroup of the diffeomorphism of X, you can think of it as a compact group acting smoothly on your manifold, and hence you know that there exist Riemannian metrics that are preserved by K. Well, at H, yeah, K invariant Riemannian metric X, then K becomes a subgroup of the isometry group of this Riemannian metric, and this is known to be a compact Lie group, well, a Lie group, if you don't want to assume necessarily that X is closed. So this is Myers-Steenrod theorem, and this is closed. Okay, and consequently K is a Lie group. Okay. Well, so I will now talk about several examples. I will try to convince you that while there are certainly manifolds whose diffeomorphism group is inner compact bounded, this is not the most usual situation. Okay? Let's talk, for example, about spheres. It turns out that the diffeomorphism group of a sphere is inner compact bounded in dimensions at most 3. Okay? Sorry? Inner compact bounded. So the existence of a maximal compact subgroup unique up to conjugation. Okay? And the proof, I mean, you need different arguments in every dimension. In R equal 1, sorry, this is an exercise. R equal 2, this is a more difficult exercise, but the idea is that whenever you have a compact group acting on S2, you have an invariant Riemannian metric. You consider the conformal class. This makes S2 into a Riemann surface. The same argument that I explained 3 days ago. Okay, and any Riemann surface diffeomorphic to S2 by the uniformization theorem is equivalent to CP1. So its automorphism group is PGL to C, and well, then you know that PGL to C is a Lie group, so it has a maximal compact subgroup, and basically this way you finish the proof. Okay. By the way, in that case, a choice of maximal compact subgroup is precisely the orthogonal group of one dimension higher. So, if you want, you can translate this property in the following terms. In the spheres of dimensions at most 3, if you have a compact Lie group acting smoothly, then you can conjugate the action with a diffeomorphism so that it becomes linear. Okay? Well, in dimension 3, the proof is much more involved. So you can prove exactly the same statement, that if you have a compact Lie group acting on S3 smoothly, the action is conjugate to a smooth action. Now, to prove that statement, you have to distinguish cases according to the dimension of the group. The most difficult case is when the group is 0-dimensional. So when we are talking about a finite group acting smoothly on S3, okay? And so we want to prove this, that so the case of dimension 0 was proved by Dinkelbach and Lieb. Using basically the results of Perelman on the Ricci flow. So it's highly non-trivial. It was a well-known conjecture in 3-dimensional geometry. Well, certainly in dimension 4, nobody knows how to control the Ricci flow. And in dimension 4, well, I will later say something else about higher dimensional spheres, but I don't know what happens in dimension 4, for example. Okay, and now on the case, if the dimension, well, this is what if the dimension of H is bigger than 0, then this is much easier. And this follows from standard arguments in 3-manifold topology. Now the next theorem is this. If the dimension of the spheres is at least 6, then the diffeomorphism group is not inner compact bounded.
7 it was more.
Sorry?
7 it was more than 1.4, but in 6 I don't know.
In 7 it was known, I see.
Yes, I know. The plenty of there is integer invariant, which is different dimensions. No, that's okay.
Yeah, okay. Yeah, that's a possibility. I mean, finding invariants, but
you have S1, many S1 boundaries.
Yeah. So this is another approach. So so you can identify OR plus 1R with the isometry group of the round metric. Okay. Now, if K is a maximal, or let's say where a maximal complex group, we could assume that it contains the orthogonal group. Okay, now we could take a Riemannian metric invariant under K. Okay. And then it turns out that this H is necessarily proportional to this one. Okay, so for example, define a function f from the projectivization of the tangent bundle of SR to R, okay, and as follows, by the condition that H of V comma V, or say, is F evaluated at the class of V, so V denotes a non-zero tangent vector multiplied by H round evaluated at V comma V. Okay, so this is really fine. And now it turns out that this function is invariant under the action of OR plus 1R. Okay? Because both H and H round are. Okay, and consequently, since the action of OR plus 1R on the projectivization of the tangent bundle of R of SR is transitive, F is constant, which implies that this metric H is proportional to the round metric, and if it is proportional to the round metric, since K preserves it, K has to be a subgroup of the isometry group, so K coincides with this guy. So what we have proved is that if there is a maximal compact subgroup, then it necessarily is the orthogonal group. Now, this implies the stating that the orthogonal group is a maximal compact group implies that any compact Lie group action on SR, is conjugate to a linear action. Okay. However,
but if you get wider case, we could assume that case is an or.
sorry, I didn't understand.
By the assumption that or is the same in
I am assuming, yeah, why can I? Okay, because by assumption, this is a maximal compact subgroup, okay? And this means that any compact subgroup is conjugate to a subgroup of K. Okay? In particular, OR plus 1 is conjugate to a subgroup. Then instead of conjugating O, you conjugate K, and you replace K by this conjugation. For any R bigger or equal than 6, Buchdal, Kvasik, and Schultz have constructed smooth actions of the alternate group A5 on SR with exactly one fixed point. Okay. Okay, but any such action can't be conjugate to a linear action, because a linear action can't have a unique fixed point. Because if it has a fixed point, then its antipodal is also fixed if the action is linear. Okay, so. Okay, so this finishes the proof. Excuse me?
How did you do it? Did they just guess some miraculous formula?
No. They use what's called equivariant surgery. So it is a very complicated machinery. I mean, there are many results of this sort in the literature of finite transformation groups. Okay, this fits into the general question of determining how much finite group actions on sphere differ from linear actions. Okay, this has been studied almost since the very beginning of the theory. Okay, and this is certainly not the first result in this direction. Okay. I don't think it. Sorry. Kvasik, yes. Yes. Okay, so how about tori? If you have, I mean, unlike spheres, tori have some non-trivial topology, or they have more non-trivial topology than tori. In fact, you have an exact sequence like this. Let me call Diff naught the kernel of this morphism. So Diff naught denotes the pheomorphisms of the torus that act trivially on H1 and consequently in the entire cohomology. Okay? Now this is, this can be identified with GL and Z. Okay? And this projection admits a section. Okay? I mean, you simply think of the torus as Rn quotient by Zn, and any matrix in GLNZ acts linearly on Rn, preserving the lattice Zn, so this induces a smooth action, and of course it makes this diagram commutative, okay? Well, now it turns out that GLNZ, at least for beacon of n, is not inner compact bounded, okay? Well, one nice exercise is to prove that GL2Z is not inner compact bounded, okay? Let me prove you that the same holds if you replace 2 by any beacon of number, okay? Sorry? Well, I mean, I take the discrete topology here, so compact means finite. Okay? Sorry? No, it's not finite, but when you consider the finite subgroups of GL to Z, they have at most 6 elements, so they are not arbitrarily large, the finite subgroups. Yeah? So it's not entirely trivial that this group is not.
Exactly, that we have an infinite number of conjuncts plus to find subgroups, right?
No.
Not necessarily. No, you don't. No.
Okay.
We have 3 classes, I think. They correspond to the singular points in the moduli of M04, I think. No, M01, M10.
Okay.
M11. Yeah. Well, anyway, let me explain how to prove that. And precisely because there is a section of that morphism of the map to GLNZ, that statement implies that the diffeomorphism group of tori in high enough dimension are not inner compact bounded. Okay? So how does one prove this theorem? What do we know about the finite subgroups of GL and Z? Well, there are many known results. For example, if one is interested only on finite P groups, then there is an almost complete knowledge about the possible size. Okay, and this is a theorem of Minkowski. So for a prime P, define MNP to be the following sum. Okay, then Minkowski proved the following. The maximal of the cardinals of the finite P groups of GL and Z is P to that number. Okay? Now, define the following. Mn to be the product for all primes P of, sorry, of these guys, okay? And let G of n be the maximal of the sizes of all finite subgroups of GL and Z, okay? And well, it is well known that this is finite, okay? But well, I will give a more precise statement now in a moment. Now, if there was a maximal compact subgroup in GL and Z, then necessarily Mn should divide Gn. It should be at least, it should be less or equal than Gn in particular, okay? Why? Well, because, if you have a maximal compact subgroup, you consider its cardinality, and its cardinality should be divisible by each of these powers, because for each of these powers, there is a finite P group of that size, and that finite group being a maximal compact subgroup, the P group should be conjugate to a subgroup, which means that the size of the maximal compact subgroup should be divisible by the cardinal, okay? Sorry?
Is it not possible to make a reduction of mod 2? The kernel is 3, the kernel is not or in any other order, and they are coprime, and we can, they are basically almost simple. No, just a question.
I'm not sure. Well, if you reduce modulo 3, if you reduce modulo 3, what you have is that the reduction map is injective when restricted to finite groups, but I don't think this implies what.
You restrict to other modules, and they are coprime. The groups are kind of different prime groups.
Yeah. I think that, roughly speaking, my argument is going to be equivalent to what you say. Yeah, I think. Okay, and but now there are the following statements. So Katz-Nielsen proved that if you divide this by n factorial and take the nth root, this converges to the following number. And then combining results of Collins and Friedman, it turns out that lim sub of Gn divided by n factorial over the un is at most square root of 6. I don't have time to explain in detail these results. The thing is that this is strictly less than that, so for beacon of n, Gn is smaller than Mn, so that's the reason, okay? Well, this implies that the diffeomorphism groups of tora in beacon of dimension are not inner compact bounded. Still, one can consider what happens with diff 0. So the subgroup of diffeomorphisms acting trivially on cohomology. I have time until 10 past, is that right? 10 past, okay. So, so now this diffeomorphism group turns out to be inner compact bounded in dimensions at most 3. So similar situation to the case of spheres. And I will not say almost anything about the proof, only that when R is equal to 3, one needs to use deep results on 3-dimensional, on 3-manifold topology by Mix and Scott. Okay. And again, in high enough dimensions, this is not ICV. Let me say something weaker. This is not ICV for infinitely many, although I'm completely sure that it depends on the existence of exotic spheres, my argument. Okay, so I don't have time to explain the argument, but let me only tell you that you can, again, when inside diff 0 of TR, you have a big compact group, which are the translations in the torus. Okay, and these play a similar role to the orthogonal group in the case of spheres. So what you can prove is that if there is a maximal compact subgroup here, it has to be the one given by translations. Okay, and now it's possible playing with exotic spheres to construct diffeomorphisms of finite order of torus, which are not conjugate to translations. Okay. I would be happy to give the argument, but there's no time for that. Let me give 2 more examples. How about surfaces? So there is a theorem by Capel, Lubotsky, and Weinberg, according to which the diffeomorphism group of a surface of genus G is not inner compact bounded. So I think that they consider the case of genus at least 2, but the statement is true also for genus at least 1 because of the argument I explained, because GL2Z is not inner compact bounded. Okay, so their proof is not so different from the argument that I have given in the case of GL and Z. So they do 2 things. First, they found a uniform bound on the finite groups acting on sigma G. This is basically Hurwitz bound that I explained 3 days ago. And then they construct by hand finite groups acting on a given surface, realizing many integers, and they prove that the lowest common multiple of such integers is bigger than the upper bound for the size of the finite subgroups here. So they can conclude this. Okay, and finally, a very stupid example of ICV manifold, manifold with whose diffeomorphism group is ICV, are asymmetric manifolds. Now let me give the definition. A manifold is asymmetric if its diffeomorphism group contains no finite subgroups except from the trivial one. Now there is a theorem. Of course, if a manifold is asymmetric, then the diffeomorphism group neither contains compact subgroups different from the identity, because if you have any compact subgroup has non-trivial finite subgroups. Okay. Now, it is known that there are infinitely many asymmetric manifolds. Okay. Sorry?
The previous theory also used that there are no positive dimensional compact subgroups, right?
Yes. Sorry? You mean in this theorem? I mean, it's relatively easy to prove that if G is bigger or equal than 2, then there is no positive dimensional compactly group acting on the surface. No, because you use Hurwitz bound. I mean, if you have a Lie group, any compactly group has a subgroup isomorphic to the circle, and then here you have arbitrarily large finite subgroups. Okay. Then, of course, if a manifold is asymmetric, then Diff is ICB, for stupid reasons, because there are basically no non-trivial compact subgroups, and there is a theorem about Schulz stating that there are infinitely many asymmetric manifolds. Well, in fact, Schulz was not the first one who gave examples of asymmetric manifolds. He proved a very general result stating that in dimensions 4 or higher, any closed manifold is cobordant to an asymmetric manifold. So there are plenty of asymmetric manifolds. Sorry? It's cobordant. It's cobordant to an asymmetric manifold. Okay, so now to finish, let me introduce, I have tried to convince you that there are non-trivial cases in which the diffeomorphism groups are ICB, but that in general, the condition ICB doesn't behave well in the smooth world. Now let me introduce a different condition. Let's say that a topological group G is compact bounded if there exists a compactly group K such that for any compact subgroup of G there exists an embedding, a monomorphism from H to K. Okay? So, of course, the big difference here is that this compactly group K need not live inside G. It is a group that exists away from G. Okay? Let me remark that the condition that K is a Lie group is crucial. Otherwise, if we only required K to be a compact group, then the definition would be void, because you could take, given a topological group, you could take the product of all its compact subgroups, and by Tichonov's theorem, Tichonov or Tichonov? Tichonov, no? Tichonov, no? Tichonov. By Tichonov's theorem, the product of an arbitrary collection of compact spaces is compact, so you would automatically get a compact topological group containing all compact subgroups of G. Okay? If instead K is if you require K to be a Lie group, this is much less trivial. Okay? Now, to be fast, let me define another notion. G is Jordan if and only if there exists a constant C such that for any finite gamma inside G there is an abelian subgroup A such that the index of A in gamma is a mode C. Okay? And now the main theorem, which I will only be able to state, is that these two conditions are equivalent. So if X is a closed manifold, the diffeomorphism group is compact bounded, so compact bounded I write CV. If and only if it is Jordan. Okay. Well, I don't have time to give details. Let me just mention one important ingredient. I mean, the main difference is that on the right-hand side, we are considering only finite subgroups of Diff, whereas on the left-hand side, we are considering compact Lie groups, so possibly higher dimensional.
Compactly, here you are Not finite. Some non-finite.
I mean, if it is of dimension, of positive dimension, it is not finite.
At least one.
No, but I also include here the case of zero-dimensional. Also included. I mean, I'm talking about general compact Lie subgroups. So finite subgroups are particular cases. Sorry?
Inversion. Z2.
Yes, for example.
Z2
Yes.
You don't need to consider infinite dimensional complex subgroups.
Where? Here. Yeah, I mean, when I speak about Lie group, I always mean finite dimensional.
For instance, is it obvious that for diff X, the diff X doesn't contain infinite dimensional complex subgroups, which would of course ruin all the properties.
Well, but I mean, if a subgroup is infinite dimensional, it can hardly be compact. Well, there is one of the ingredients of the proof is a theorem of Lie, but not LIE, but LEE, which says the following: for any compact Lie group K, there exists, or let's call it H, there exists a finite subgroup such that, which surjects onto pi naught, in the sense that, so you are given a finite Lie group, a compact Lie group, sorry, that a priori may contain different connected components. You can find always a finite subgroup that meets all connected components, okay? And this is the basic idea connecting finite subgroups with compact Lie groups in general, okay? But, well, anyway. Now, what we have done is to translate this condition into this. This is not an easy condition to study, but we know nowadays some non-trivial information. In particular, we know that diffeomorphism groups of spheres are compact bounded. I mean, we know that they are Jordan, so by this theorem, they are compact bounded in all dimensions. The same for tori. Okay, so unlike what happened for the condition of inner compact bounded, here the condition is satisfied in all dimensions. The same for surfaces.
So H, for example, H is equal,
Yes.
So we are saying that, for example, there are no, let's say, there are subgroups without elements of order 2. It may be well possible that any subgroup, let's say, two group.
Let me see. So
I don't understand. Z3 and Z2, how they, suppose you have automorphism of order 2 and order 3.
the only thing that this is claiming is that you have outside of your diffeomorphism, you have a compact Lie group that contains all groups that act effectively on your manifold. So, for example, the circle contains copies of Z mod 2 and Z mod 3.
Okay.
In this sense.
Okay.
Yeah, I mean, it is a much weaker condition that inner compact bounded. Okay? So, and to finish, just to prove that this condition is not always true, which probably would mean that it is too weak a condition, there are examples of manifolds whose diffeomorphism group is not compact bounded. Okay? So, the diffeomorphism group of T2 times S2 is not compact bounded because it is known not to be Jordan. Okay, so this is a theorem of Chikosh, Piber, and Szabo. Sorry?
GLN of Z, which was not uniform.
It is also, yes, absolutely, absolutely, yes. GLNZ is compact bounded, precisely because you have a uniform bound on the size of its finite subgroups. Okay? Okay, so I stop here.